So, hello everyone. Welcome to the seminar. I hope you can all hear me. If you can't, then please let me know in the chat. The people of you who might not know me, so I'm Christoph Bergmeier. I'm a Maria Zambrano Senior Fellow in here in Granada, so in DaSCI, and I'm in Granada. I'm very happy to present today our speaker, who is Daniel Schmidt, an associate professor in computer science in the Department of Data Science and AI at Monash University in Melbourne, Australia. He's a long time, well, by now kind of long time friend and collaborator of mine. He does lots of interesting work, so he has technically a background in computer science, but he's also done a lot of statistics. He worked a lot in kind of also genomic statistics. And I think he has a very interesting talk for us today, which is prevalidated rich regression is a highly efficient drop-in replacement for logistic regression for high-dimensional data. So, for who of you are wondering, Daniel is actually with me in the room here, sitting right next to me. So, over to you, Daniel.
Thank you, Christoph, for that introduction, and hello, everyone. I hope you can hear me and see me. Yes, so I'll just make that full screen. And yes, so today I'm going to be talking about a way essentially of fitting high-dimensional logistic regressions very quickly, and also getting out of them at the end reasonably or well-calibrated probabilities, but fitting them essentially very, very quickly using a technique called pre-validation. So as Christoph mentioned, I'm from Monash, and I've known him for a number of years now. And this work here has been done with in collaboration with my postdoc, Angus, and another collaborator of mine, Jeffrey Webb, a machine learning person from Monash, well known in Australia. So I guess I should get started. So we're going to start off by reviewing multinomial logistic regression as a linear classifier system. And then we're going to talk about ridge regression classification, so effectively approximating multinomial logistic regression via least squares. And then finally, we're going to talk about pre-validated ridge regression, which allows us to get probability estimates even when we have huge numbers of features without changing the overall time complexity of this much faster ridge regression classifier. And if time permits, which it probably won't, there are some technical details pushed to the end about how we maintain the speed of this linear approximation, even when we move to computing probabilities. So, as a motivation for the work, one of the things I work in is in this field of scalable time series classification. So in this setting, you have your input features, if you want to call them that, are time series, and your targets are classes. And while the work in here is not specific to that problem domain, it was one of the motivations. And the reason is because one of the key methods in this space is based on large numbers of random features. And it's many times faster than competing methods, but one of the reasons it was so fast is that it uses the ridge regression classifier to fit the linear classification layer at the end, which is a type of least squares approximation to multinomial logistic regression. And its advantage is that it's very, very fast to fit because it's based around least squares, but the disadvantage is that it does not produce probabilistic predictions by itself. And while there are a number of techniques for calibrating or turning non-probabilistic predictors into predictors, we wanted a method that A, worked when you had many, many, many features, and B, did not change the time complexity of this very fast ridge regression classifier. So the aim was to produce probabilistic predictions from the ridge classifier without affecting the overall time complexity. So, as a quick review initially, we'll talk about linear classifiers. So in the classification problem, we have a vector of targets, themselves being integers, say from 1 to L. Without any loss of generality, we can assume the L different classes are just labeled 1 to L. And we have a N by P feature matrix. So N is the number of individuals or observations, and P is the number of features. And the aim is to predict which class an individual belongs to based on their features. So linear classifiers specifically are classification systems that are based around linear predictors of this form. So we say that eta, the linear predictor, is equal to a linear combination of the features and some weights, our regression weights. So the linear classifiers use linear predictors in some fashion. And linear classifiers are very popular for a number of reasons. One is that they're very relatively simple to understand and fit. Another is that they, in some sense, suffer less from the curse of dimensionality because of the strict linear assumptions. So they can work very well when we have large numbers of features. And to that note, if you have suitable features, they can obviously perform very well with relatively low variance. So they are very useful. And of course, the final layer of most deep neural networks is a linear classifier. If we froze all the weights down the chain, we would end up with just having a linear classifier of a bunch of derived features. So the standard, let's say, linear classifier, probabilistic one at least, is the multinomial logistic regression. And it's obviously a very old model. It's been around for a long time, but it's still very useful. So if we let beta, say, of I denote the coefficients associated with class I, then we can form L different linear predictors, one for each of the classes. So we have L sets of coefficients and single feature matrix. We form L different linear predictors, which we concatenate into a matrix, say H. So we have this N by L matrix of linear predictors, one associated with each class. And under the multinomial logistic regression model, what we do is we squeeze these linear predictors through what's now called the softmax function, so a logistic squashing function. So the probability that an individual, say I, is in class J is equal to E to the linear predictor for that individual for that class, divided by the sum of E to the linear predictors for that individual for all the classes, which normalizes this to be a probability between 0 and 1. And there's a number of reasons logistic regression is popular compared to other forms of squashing functions like probit regression, for example, a number of different reasons. One is the very clean interpretation. We can interpret the linear predictor here as the log odds in favor of one class compared to the others. So this gives us a probabilistic statement about what class an individual is in, given a collection of weights and a feature. And what we can do is we can form the negative log likelihood of our observations, Y, our targets, by taking the negative logarithm of the probability assigned by this formula to each individual, depending on what class they happen to be in. And after a little bit of simplification, we see that the negative log likelihood has this form. We sum over the individuals, we have minus the linear predictor for that individual, depending on what class they're in, plus log of the sum of the exponentials of the linear predictors for all the other classes for that individual. So we've got this negative log likelihood, and if we want to fit our model to the data, so we want to choose a set of coefficients such that the logistic regression assigns high probabilities to those classes that the different individuals are in. And one way we can do that is through maximum likelihood. So we could minimize the negative log likelihood. So we could take this negative log likelihood function, which is itself a function of these L vectors of coefficients, and we just optimize this function until this should be a min here, until the negative log likelihood is minimized or the likelihood is maximized. So we find the values of the coefficients that assign the most probability that we can to our observed data. And this process, maximum likelihood estimation, has several advantages. One is that the choice of the logistic squashing function means that the problem is convex. So there's only a single minima if a minima exists. And another is statistical advantage, which is that asymptotically, these estimates are statistically efficient. What do I mean by that? So I mean that for large sample sizes, they extract about as much information out of the data as is possible. And they have the smallest variance in the limit as n goes to infinity. Now, if the number of individuals is smaller than the number of features in our feature matrix X, then it turns out that there's no unique minimizer for this equation. We'll simply be able to separate the data. And so the solution, if there was one, is to push all the coefficients to plus and minus infinity, so into these boundaries. And even if n is, say, so even if n is bigger than p, if n is close to p, so if we have similar number of individuals as we have features, then the estimates, they might exist. The solution to this might be unique, but the estimates can have very high variance. So these problems can be solved and are solved frequently via regularization. And there's lots of different regularization schemes. We're going to consider L2 or ridge penalized maximum likelihood. So in this process, we augment our negative log likelihood with a penalty term here, which is the sum of the L2 norms of all the L different coefficient vectors times lambda, some hyperparameter, which is the degree of penalization. So ridge regression is nice because if many of the features are weakly associated with the targets, so that we expect, say, most of the features to have some minor association with the target, then ridge regression will work very well. Ridge regression doesn't work particularly well if the underlying coefficient vector is assumed to be sparse. That is, if we assume most of the features to be unrelated. But in the problem we're looking at, where we're generating random features from time series, we noted that in general, most of the features tend to be weakly associated, and ridge regression performs very well. So adding this penalty resolves the issue of non-uniqueness of the minimizer when we have n less than p, but introduces a new issue, which we now need to choose a value for lambda, the hyperparameter, and this is frequently done via k-fold cross-validation. Now, there's no closed form solution to the penalized, or in fact unpenalized ML problem here, the maximum likelihood problem here. We can't, if we differentiate with respect to beta set to 0, there's no simple closed form solution. So what we need to do is find the estimates numerically. And there are a number of different algorithms in the literature for this. Standard ones include the iteratively reweighted least squares or Fisher scoring algorithm, which is the one implemented in scikit-learn. And of course, you could use stochastic gradient descent or some other stochastic search as well. But these two are probably the most common in the literature. And this numerical search can actually be quite difficult, or at least slow for very large P. So if we have, 20,000 features and 15 classes, we have to adjust. I should have said 10 classes because my arithmetic's no good. If we have 20,000 features and 10 classes, we have 200,000 free parameters we need to optimize. So we have large numbers of parameters to optimize, and the correlation between the weight vectors can affect the convergence speed for large L. And what I mean by that is, of course, that the weight vectors must be correlated, because if you boost the log odds of one class, then the other classes will be affected. because of the correlation between this multinomial random variables. Only one thing can be on at any one time in a multinomial. Additionally, if we use k-fold CV to choose lambda, so if we try and choose the regularization parameter by using k-fold CV, which is a reasonable strategy, then we have to run the algorithm, say k times r times, where r is the number of candidate values of lambda that we want to try, and k is the number of folds we're going to use. So now we have a potentially slow optimization problem being made even slower by the fact that we have to rerun it multiple times. And the final model you end up with can actually be quite sensitive to the particular k-split that you take. And we actually see that in practice, in the results, that the k-fold cross-validation solution to this problem can have occasionally quite poor performance because, well, classification or multinomial data, the individual data points don't contain a huge amount of information. And so if you have rare, or even with stratified sampling, you can still find that the final model can be quite sensitive to the particular split that you choose. Now, that can be moderated by doing multiple CV repetitions, but now we have another factor of, say, m repetitions that we need to run the whole process for. So it can be all quite slow. So as an alternative, people sometimes use least squares or ridge regression to build classifiers. So the idea here is that if we only want class predictions and we're not interested in probabilities, then we could speed the entire process up that I just described by using approximate solutions for the weight vectors based on some form of penalized least squares. So if we're going to use least squares to fit a classifier, what we need to do is we need to take our targets, which are integers, 1, 2, 3, 4, 5, etc., and recode them in some way, because of course, they are simply nominal values, 1, 2, 3, 4. They could be A, B, C, D. There's no arithmetic connection between the values. So we need to recode them so we can use least squares. And the standard technique is to build a one versus all system. So for each of the different classes. So what we do is we build a new target matrix, which has L column vectors, one for each of the classes. And inside this columns, we say that, say, the target for individual I class J is equal to 1 if the individual is in that class and -1 otherwise. The particular values plus and -1 are completely arbitrary. They don't affect anything, but we pick 1 and -1 simply for symmetry and presentation. So for example, if our target here was individual 1 was in class 1, we would say that they have a 1 in the first column, -1 everywhere else. If they're in class 2, an individual, they have a 1 in the second column and a -1 everywhere else, and so on. So we turn our n by p target vector into a matrix of n by l, one for each class. And then what we do is what is done in the packages, for example, in Python, the ridge regression classifier. What it does is it fits L separate ridge regressions to each of these new targets. So in a ridge regression, we are doing least squares penalized again by the L2 norm. So we find the value of the weights that minimizes the residual sum of squares to our new target vectors plus some hyperparameter times the L2 norm. And the nice thing here is we've transformed the problem from one that has no closed form solution into one that has a very well-known closed form solution. So the solutions given lambda to this least squares problem, penalized least squares problem here is of this form. We take our feature matrix, form the gram matrix, so X transpose X, add an identity times our hyperparameter here, invert that and multiply by the inner products between the features and the targets. And this gives us the solution to this optimization problem. So that already speeds things up dramatically. There's no need for a numerical search. We can use standard least squares solvers. The second thing that makes the whole process quick is to choose the regularization parameter. What we can do is we can exploit the fact that for leave one out cross-validation with least squares and linear models, there is a very clever shortcut trick So we can compute all of the least squares, leave one out, cross-validation errors in the same time it takes to do a single least squares fit. So this means we don't have to refit the model, say, n times. So transforming the problem from a multinomial logistic regression to an approximate solution via least squares makes things very quick. And once we've found the feature vectors for each of the new pseudo targets that we've created, if we get a new feature vector, we can classify that individual by simply computing the inner product between the feature vector and the weights for each class, and taking the class with the largest predictor as the one that we are going to classify them to be in. So the problem here, of course, is that this approach only provides predictions of classes and doesn't provide estimates of the probabilities of being in classes. So why are accurate probabilistic predictions useful? Well, imagine if we had two different feature vectors, say x1 and x2 from two different individuals, and the probabilistic classifier, say, assigned the first individual to have a 45% chance of being in class 1 and a 55% chance of being in class 2. And the second classifier said there was a 5% chance, say, the individual was in class 1 and a 95% chance the individual was in class 2. So if we use some sort of maximum probability rule, then both would classify the individual, say, as being in class 2 because they're more likely to be in class 2 than class 1. But of course, if we look at the probabilities, we see that the classifier is much more confident that the individual is likely to be in class 2 in case number 2 here than in case number 1. Here it's rather borderline. If you have to make a guess, maybe you choose class 2. The second case, the probabilities tell you that the classifier at least is very confident that you're in class 2. So obviously non-probabilistic classifiers would just return class 2 for both cases, and they would lack this extra information. And that information can be useful because you could use it, for example, as an example, to do some sort of minimum expected loss classification. If you could assign losses, monetary or otherwise, to incorrect and correct classifications, you can use decision theory to make minimum loss decisions. So there is obvious value in having probabilistic classification. So what we've got here is we've got a bunch of weight vectors that we've learned by least squares approximation to the classification problem. And for a new individual, we can calculate the linear predictors for each individual based on these weights, and we can choose which class they're in by choosing the linear predictor with the largest value. So we might try and post hoc create probabilities for the ridge regression classifier. So what we could do is we could take the linear predictors for all the individuals for each of the classes, the ones that we've learned by ridge regression, and we could pass them through the softmax or the logistic transformation and maybe scale them by some scalar kappa and say, well, okay, these are our linear predictors. They're not the exact linear predictors we would get from maximum likelihood, but maybe they're close enough. So if we take them and scale them by k and adjust k until we minimize the negative log likelihood, we might be able to calibrate the linear predictor, right? So you could think of this as kind of a restricted maximum likelihood estimation. We choose the minimum negative log likelihood solution, but from a set of solutions which are constrained to be solutions to a least squares problem. And if the number of features is much smaller than the number of individuals, this actually works pretty well. Right? And the reason is in this case, the data in general will not be perfectly linearly separable. And this likelihood here provides us information on which we can use to estimate this calibration factor kappa. So this is one way of creating probabilistic predictions from non-probabilistic classifiers. There are several others. I won't go through the whole detail. Maybe if people are interested after, I can explain also why the other techniques don't work in this case. But that's cutting, I guess, to the chase a little bit. So the problem is if P is very, very large, then this naive process or simple process, let's say on the previous page, doesn't really work. And unfortunately, when P is large, that's generally the setting where linear classifiers are useful, right? So it's important to try and make sure that we get it to work in these settings. So as a general rule, we're going to have a large number of features, especially in the problems we were looking at where we had random features from our input time series. We had thousands and thousands of them. And we needed thousands because each of the random features tended to contribute only a little bit of information predictive towards the class. So more features was very useful. So it was important to try and get it to work when we had more features than samples. And the reason it doesn't work when P is very large is that in this case, when we have many, many features, only many, many more features than samples, the linear predictors from the ridge fit, they tend to fit the training data extremely closely and perhaps not exactly perfectly, but they appear to be almost on the surface to be a perfect fit in the sense that if you looked in the training data, you would see that the linear classifier or the linear predictor associated with the class that an individual is in would be the highest for that class. So you would get perfect in-training classification. Now, due to the regularization, when you move to a new data point that's out of the training data, you actually can still get good predictions. Even though you're perfectly fitting the training data, it doesn't necessarily mean you're going to overfit heavily onto future data. And this, I guess, is an example of this benign overfitting phenomena that's being discussed recently. But the problem is, if our linear classifier fits the training data perfectly, then that means that when we pass the linear predictors through the squashing function and try and adjust for kappa, all that happens is we make kappa as large as possible because for each individual, the linear predictor associated with the class they are in is the largest. So we might as well just push kappa to be as big as possible to assign 0 and 1 probabilities to all the instances. So that's fine on the training data, but of course, when you draw a new data point, you're unlikely to perfectly classify it. And the log loss on future data is going to be extremely high if we are assigning all individuals either probabilities of near 1 or near 0 of being in the different classes. So that takes us to the crux of the idea, which is prevalidated ridge regression. So the problem here is that or perhaps one of the main problems is that the regularization being done when we do the ridge regression classifier, the regularization is being done with respect to the squared error fits, not the log loss itself. And then the subsequent calibration step we do after takes the predictions made by these ridge classifiers and plugs them in and treats them as if they are somehow exactly the population estimates of the log odds for each of these individuals. But of course, they're not the population values. They're just estimates of the population values. And as such, they have with them a degree of variability or uncertainty about them. So what do I mean by that? I mean that if you resampled a collection of data from the same source and fitted your ridge regression again, you would find that the estimates that you end up with would be different, right? They're going to vary from sample to sample. And the uncertainty or variability in these estimates can be very large if P is much greater than N. You can have quite a large degree of variability because the individual values, say, of each weight value are not particularly relevant, just their linear combination is relevant. So what we're doing here is we're using the same data to calibrate that we were using to fit the classifier. So what we wanted to do was somehow account for this uncertainty, but do it in a quick fashion. We didn't want to change the time complexity of the problem. So that was a really key aspect in the decisions that we made. And ideally, what we'd like to do is to choose the degree of regularization based not on the squared error, because that ultimately isn't the loss that's relevant, but on the log loss itself. So there are lots of different ways you could try and account for uncertainty. So standard techniques might be, for example, bootstrapping, where we redraw, we treat our sample as a population and we resample from this estimate of the population, refit the models. We didn't use that because it's quite expensive in the sense that if you draw a new sample from your samples, if you resample, you need to recompute all the quantities, refit the models. So we wanted to avoid that. You could also perhaps do some sort of Bayesian sampling or averaging, something I'm still looking at. But what we ended up doing was looking at using leave one out cross-validation. And the reason we chose leave one out cross-validation is twofold. One is that it's related to the technique called the jackknife, which is a form of linearized bootstrap. So it has some nice theoretical properties. And the second is that it has a bunch of computational advantages. So we were able to take into account the uncertainty in our estimates without changing the time complexity of our algorithm. So what do we do? Well, instead of using the linear predictors based on the ridge regression fits to the data, and then passing them through the softmax and calibrating, what we did is we used the leave one out cross-validated predictions instead. So what do I mean by that? Well, if beta hat of j minus I, if that's the ridge regression solution for class J, regularization parameter lambda when we drop observation I from our data, so we drop person I and fit our ridge regression, we can then take that cross-validated ridge regression weight vector and predict what the individual's linear predictor would be when we take the left out individual, we use their feature vector with the beta vector based on the data with them left out, and we predict. So this is our cross-validated linear predictor. So what we do is instead of taking the linear predictors based on the ridge regression fits, we take the cross-validated linear predictions. So we drop each individual one at a time, fit all the ridge regressions, predict their linear predictor, do that for all individuals. So we end up with the same N by L matrix, but now the predictions are based on dropping individuals from the data. And we can call that matrix, say, H tilde. And these are called pre-validated predictions. So the reason we call them pre-validated is because as we were doing the work, I discovered a paper from the mid-90s from Robert Tibshirani, like half the papers, it seems, in statistics seem to come from Robert Tibshirani. And they had used this idea of using cross-validated predictors for a totally different situation and a totally different problem in genomics, but they had used this idea to get around the fact that you don't necessarily want to collect a whole fresh set of validation data. So we call them pre-validated predictors based on this previous work. So if we want to connect back these pre-validated predictors to the usual ridge regression, the quantity here, the sum over our eaters here, our pre-validated predictors, and the pseudo targets that we created, sum squared would be the leave one out score that we would normally optimize with respect to lambda. But rather than just computing the score and adjusting lambda based on this squared error loss, what instead we're going to do is take our pre-validated or cross-validated linear predictors and squash them through our softmax function. So now we have this nice little maximum likelihood or minimization of negative log likelihood problem where we have a scaling factor kappa to calibrate our pre-validated predictors, but we can also adjust lambda, the amount of regularization, as part of this same process. So because as we change the value of lambda, we change the ridge regression solutions, and therefore we change the pre-validated predictors. So if lambda gets larger, most of the pre-validated predictors will get closer to zero as the predictions get shrunk more to the mean. And if lambda is small, then the pre-validated predictors will be closer to the leave one out least squares predictions. So what does this reformulation achieve? Well, this matrix here of pre-validated predictors is a perturbed version of the predictions that you would get just on the training data. So it no longer provides perfect fits to the training data. And what that means is that there's now information in this matrix to allow us to estimate kappa from the negative log likelihood. We don't get perfect fits, so kappa won't just zoom off to infinity to provide a zero negative log likelihood. The other nice thing is, as I mentioned, the regularization parameter lambda was now chosen not to minimize the sum of squared cross-validation predictions or errors, but rather the negative log likelihood that we would expect under resampling. So once again, you can kind of think of this approach as a type of restricted maximum likelihood estimation. Rather than allowing the weights to take any values in RP, we now restrict them to be scalar multiples of the squared error ridge solutions. And the nice thing here is at the end, we end up adjusting only a single free parameter kappa numerically rather than L times P parameters, as in the case of full maximum likelihood. So that's the basic idea. And as I mentioned, the reason we chose leave one out, it's important because we didn't want things to be any slower than the standard ridge regression classifier. And this is the case if we choose this leave one out approach. So an important aspect of the whole thing is that it's very fast and exploits a number of linear algebra tricks to achieve that. I give a very brief outline of the process here, and then we'll discuss some results. So the key idea here is if we let M be the maximum of NP, so whatever's larger, N or P, N is the number of individuals, P is the number of features, and R is the smaller of the two, and we assume that the number of classes is smaller than the smallest of these two, which is reasonable. You know, if we have 1,000 classes and 40 data points, there's no information to learn the relationships. And so that's I think a reasonable assumption. So the key ideas that keep things fast are the following. We first note that each linear predictor uses the same feature matrix X. So anything you do to the feature matrix X only has to be done once. So what we can do is we can perform a singular value decomposition on this matrix, which has time complexity MR squared. So the time complexity of a single least squares fit. And at the same time of doing this SVD simultaneously does two things. It performs dimensionality reduction and orthogonalization. Basically, we can transform our matrix down into an N by R matrix, where R is the min of N and P. Now, the orthogonalization is useful because the ridge solutions for a particular lambda can be computed in effectively linear time if we have orthogonal design matrices. So if the features are orthogonal to each other, then ridge regression becomes very simple. And we can modify the leave one out cross-validation shortcut in an interesting way to, rather than give us the cross-validation score, which it normally does, we can compute the actual predictions, the leave one out cross-validated predictions in LR squared time, as long as the design is orthogonal, which it is by the SVD. So at the end of all that, the dominant term here is just the SVD, which of course is the same time complexity of a single least squares fit. We used another technique like Cholesky decomposition or whatever. So in the end, all the additional bits that we add on don't increase the time complexity in any meaningful fashion. So that was kind of all of these moving parts had to sort of be put together. And, you know, a key aspect of it is the fact that the leave one out specifically has these shortcut formulas. But once you sort of piece them together, you can get a very quick implementation. So just as some results here, I'll go through some results. So we ran our algorithm on a number of data sets that we collected. Well, when we say we, I should say Angus collected and managed to find all these data sets. So we found 95 data sets, which we might call, say, tabular data. I think they're mostly discrete predictors. And they were larger N problems, with N ranging, the number of individuals ranging from 500 to, say, 940,000, and smaller P problems, so 4 to 500 predictors. And what we did is we augmented these with also all these second order interactions, trimming the design matrix if it exceeded 4 gigabytes in size. We also grabbed some small n large p problems, so microarray data. It's from the genomics space. And they tend to have small numbers of individuals because people are expensive, and large numbers of measurements because measuring people is cheap. So we had 72 microarray data with n from 12 to 300 and large p, so 12,000 to 55,000. And the last one we used was our time series classification problem, so 106 data sets from the UCR, which is the repository time series sort of benchmarking repository. We restricted ourselves to data sets with 5 or more examples per class, and we generated for each of the problems 10,000 random features for each of the individuals. And then what we did is we fitted linear classifiers using our calibrated pre-validated ridge regression, i.e. the method we've presented here, Preval, and L2 regularized maximum likelihood with 5-fold CV using the scikit-learn implementation. To implement our code, we have our own package. It's available at the end, and we evaluated the 3 on classification loss, log loss, and also wall clock time. So if we look at the tabular data, we see that we have here a plot of, we called it in quotes, logistic regression here is our penalized maximum likelihood, 5-fold CV. On the x-axis, pre-validation is on the y-axis, and the dots represent the classification accuracy achieved for each of the classifiers on each of the problems. So we can see that in general, the classification accuracies lie on the diagonal line, so there's not a great deal of difference between doing exact maximum likelihood estimation or this approximate maximum likelihood estimation via our pre-validation technique. If we go to log loss, so we have the same idea, except now the axes are the logarithmic loss on the data. So we use our classifier to predict a probability distribution over the multinomial and then score based on what probability is assigned to the actual class label. And we see that overall, again, the trend is roughly a diagonal, but it's a bit more spread out, which is what you might expect with logarithmic loss, because of course it's much more sensitive than 0-1 loss. You know, if you have 1 or 2 small or poor estimates of probabilities, you can have quite an impact on your mean logarithmic loss. But overall, the 2 methods seem to perform quite similarly. We then looked at training time, and you can see the substantial difference between exact logistic regression, say using penalized L2 penalized maximum likelihood with 5-fold CV versus our Preval system based around least squares. So you can see that the speed ups are in order of anywhere from 10 to almost 1,000 times faster, with the average speed up being around 10 to 100 times faster for these problems. For the microarray data, we see that the tail of the classification loss is similar. There's not a great deal to tease the 2 methods apart, but logarithmic loss exhibited this interesting property that there was a large number of data sets for which the performance was very similar between the 2 methods, but the exact maximum likelihood or penalized maximum likelihood estimation could suffer occasionally from very large, relatively large logarithmic losses compared to the pre-validation scheme based on least squares. And while we're investigating this still, it appears most likely that it's simply a factor of sensitivity to the particular folds that you use when you're doing 5-fold CV, particularly if the number of individuals is not that great. So it seems that just occasionally the models choose a regularization parameter from the CV that actually just isn't very good when you're predicting onto future data. Now, as I said, this probably could be moderated by taking multiple CV repetitions, but of course this would drag the speed down even more. Anyway, it's an interesting CV in general, of course, cross-validation in general, of course, is much more sensitive to sparsity in design matrices than other methods that use all of the data, because you are dropping individuals. So if you drop individuals that contribute a large amount of information to a particular class by chance, you will have high variance in your cross-validation scores. And in this case, because P was so much bigger than N, we see substantial, very substantial speed ups over the scikit-learn implementation, up to 1,000 times or over 100 times on average faster. So fitting was many, many times quicker, while the accuracy was virtually largely identical. And we also had similar results for the time series with similar story and a similar sensitivity occasionally to poor choice of lambda. And again, a similar story in terms of speed up. The final results I'll present was some learning curves based on the MNIST data. So in this case, what we did was we took the MNIST data and we did random features extracted from, so random convolutional features extracted from the MNIST digits, and we changed the number of features, and then for each of the number of features, we increased the number of data to produce these learning curves to show how the methods perform as you get the more samples with a fixed design matrix size. And on the plot, we see that dark blue is our pre-validation scheme, so least squares or penalized least squares, that's pre-validated and calibrated. The orange is penalized maximum likelihood or logistic regression. The green here is the ridge solution passed through the squashing function, the softmax, without any scaling. So this was just a sanity check to see was there actually any point to doing all this pre-validation and calibration if maybe it just worked perfectly well without doing any of it. And we see that the least squares or the ridge regression fits here provide very little information, probabilistic information about the data without some sort of scaling. The aura red one is an interesting line. That is the ridge regression fits scaled without pre-validation. So we see that when N is large compared to P, they can actually perform reasonably well. So there's not really much of an advantage to doing our pre-validation. But what we see is that when N and P are close, it exhibits a type of double descent phenomenon. And that's because as N gets close to P, the calibration factor kappa will get close and closer to infinity, and it'll put more and more probabilities onto, or mass onto one of the classes against all the others. And then as N gets larger, it eventually starts to perform again. What we thought was really interesting is that while our pre-validated approach tends to, as one would expect, be less competitive with maximum likelihood when N is large and P is small, we see that it's actually very competitive, even though it's only doing this form of restricted maximum likelihood. It's very competitive when you have large numbers of features. Now, I will caveat that all by saying that for large P, we might be competitive, but if we had really, 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 really large N, we would expect logistic regression to beat our method every single time in terms of performance, because logistic regression is based on maximum likelihood, which is asymptotically efficient. If you're not using the likelihood when your N is large, you cannot be asymptotically efficient. So we don't use the exact likelihood, we use an approximation to it. So we would expect a very large N. You would just prefer maximum likelihood. But in the settings that we're working in, where P is much bigger than N, we see that the behavior is very nice. And another thing, we see that the learning curves are very stable. That's because the model fits are all based on these restricted least squares coefficients that are just scaled once, and the least squares ridge regression solutions are extremely stable to permutations of your data. If you drop or add data points, the solutions change very little. Whereas logistic regression maximum likelihood is, of course, notorious for being reasonably unstable when you have not too much information about each of the classes. Cool. And that, I think, can conclude things. I'll leave the technical details. They were in there for another talk. They're just a bunch of linear algebra anyway. So we can get to the end. If you're interested in the code, the package is available at GitHub. You can grab it and run it and try it on a problem. And even if you're not, thank you for your attention. Thank you.
Thanks. Good talk. I'm over here so that we don't have to fiddle around with the mics. Yeah, very interesting talk. Thanks. Do we have any questions? So if anybody has any question, either pop it in the chat or just open your mic and speak. Well, otherwise, while people are still gathering their thoughts, so one question that came to my mind was, you know, I mean, obviously, like people are very used to these very complex neural network type of methods, and so for them, it's maybe the question, well, like a logistic regression, a rich regression, that sounds like something that is already quite fast, right? So the question is, how meaningful do you think are these speed ups actually in practice?
Good question.
Yeah.
Right. So I guess it's motivated for us from this scalable time series sort of setting where if you can squeeze a fit from being 5 minutes to 2 seconds, then you can apply it at much bigger scale to much larger numbers of time series. So this is the primary consideration. So that's why we're happy to sacrifice a little bit of potential accuracy for a substantial speed up. But yes, of course, I mean, outside of that, perhaps it's not so super relevant, but
yeah, I mean, I think I remember, you know, people would do quadratic features and like all sorts of transformations on the features and then feed it into logistic regression.
Yeah, so that's exactly the sort of situation where you would use this type of thing. So that was in the examples there, we were doing exactly that. And you can actually get pretty good performance relatively quickly from these type of features as well. Right? Even with the MNIST, okay, you don't get, say, state of the art, but you can quickly get into the high 90s with just a bunch of interactions between random convolutions and be extremely fast.
Okay, we have some questions in the chat. So Aurora, do you want to ask a question?
Oh, there is one. Oh, sorry. Yep, Aurora. Yes. Hello.
Hello. Thank you so much for the talk. Very interesting approach. And I was wondering if you have studied this applied to online learning, if you are familiar with the.
I am familiar with the basic ideas. No, we haven't looked at online learning. That also seems like a sort of situation where things could be useful to be faster and faster, right? So especially if you have multiple streams of data or something. But no, we haven't looked at that. But that's an interesting idea, actually.
Yes, the idea is because I don't know if there is a static training part that you should do before applying the method. That was my question.
Yeah, so I guess the interesting thing is you have the SVD, but you should be able to do online updates of the SVD, or at least approximate enough as you get more data. So you probably wouldn't even have to do the whole SVD each time. So it actually could work quite well for online setting. That's something to investigate. I would never have thought of that, to be honest. So that's an angle that I hadn't thought of. We were thinking about the idea of adding more features iteratively and doing an update, a vertical update, but I never thought of doing a horizontal update, as it were, to the SVD. So that's cool. Thank you.
Okay, thank you.
We have another question.
Yeah. So yeah, that's an interesting question. So we used five-fold CV because it's the standard default in the package. I'm not, I guess, want to stress that I'm not claiming that you couldn't optimize the performance by choosing different folds. And leave one out would be a lot more stable, I imagine those. So my guess is that if you use leave one out cross-validation for logistic regression, obviously it'd be very slow. But there is some paper where there's a way of speeding it up somewhat, which we were alerted to by someone, but it's still many orders. It's several orders of magnitude slower than our package. But if you did use leave one out, I would expect things like this here to disappear. So I think these occasional poor performances in log loss are probably artifacts of 5-fold or 10-fold CV, and that if you leave one out, they would be removed or disappear from the plot. That would be my guess. Because it's interesting, you notice that the classification scores here are virtually identical, but the log losses can be quite different. And that's just because, you know, you can have two models with the same classification score, and if you scale one up too much, the predictors, they will just have bad log loss. But yeah, that's an interesting question, but I think that's what you would expect to see. A lot more stability from the maximum likelihood fits.
Okay, thanks. Do we have any other questions from anyone? Last chance to get a question in.
So as I said, if anyone's interested, there's
exactly. So here we have
code and the archive paper. If people are interested in giving the package a run, it's all nicely optimized up. And we even found a quicker way of doing the SVD than the defaults. So like the Python SVD can be sped up in this particular case. I'm surprised they don't use this alternative formulation, but.
Okay, that's good. Okay, good. Well, we are pretty much at time. 1 minute left, so I think probably let's leave it there. I thank Daniel again for the.
Thank you for attendance, and I hope that you found it interesting at least. And I wish you all a lovely evening. Thank you.
Thanks. Bye.
Thank you. Bye.